Welcome to the lecture series on reinforcement learning. In this video, we'll discuss change point detection with a base factor surprise. Here in this little image on the left, you see observation points, little black dots. I've circled one of these, and I will remove the gray screen. And so as a function of time from left to right, more and more dots will appear. And your task is to predict the location of the next black dot. Let's try to do this. Okay, that's it. Now, we try to make predictions, and then we realize, well, our predictions are wrong. There are certain abrupt changes that occur rarely with small probability. These are called change points. So change points are at these locations indicated by the red arrows. So how did I generate these black dots? Well, it's a non-stationary stochastic process. And the idea here is that they are drawn from a Gaussian distribution. The mean of the Gaussian is fixed for many steps. But then the mean jumps at the change points with very small probability. The variance is fixed. And the task I gave you implicitly was to estimate the momentary mean of this Gaussian. Now, if you know that occasionally there can be change points, then basically you have to reset your model after each change point. Knowledge you have acquired no longer makes sense once you are beyond one of these change points. And so at the beginning, you know, well, I told you dots will appear in this region here. So you have a prior between -4 and 4. You have seen the first few data points. So you know this is where dots will appear. And then as you follow the evolution of these dots, you get more and more sure that the mean is in this region. So your prediction narrows down to a small region. But then we have this change point here, and now it turns out in this kind of volatile environment, the best approach in a Bayesian sense is you reset your belief to the prior if the observation does not make sense. So once you discover the change point here, you say, well, dots must appear somewhere, but then again your belief will quickly narrow down to the new situation. But then there's another change point, and again you start and so forth. And now throwing away the old model means the plasticity of the system must increase if you have this surprising observation, and the surprising observation is caused by a change point. So the plasticity of the system must increase. Another way to say this is we have to implement a reset by increasing the learning rate. And so now if we have a surprise measure, then we can say this learning rate or this amount of reset should increase as the surprise increases. So it's a monotone function of the surprise. And this is indeed true. So we can look at the new belief, sort of what kind of mean theta would you say once you have integrated the next data point? And you can integrate this starting with your current belief, your old belief at time t, then you see the new data point at time t+1, you integrate it with a standard Bayesian formula. That's this p integration. But then you know we are in an environment where there are change points, then occasionally you should reset to your prior belief and use this new data point as the first data point. So you restart integration. After a reset, you restart with this prior probability P0. And now, so you have two different terms, and you give them a weight gamma for the term with the reset and a weight 1 minus gamma for the other term. So you want to reset your belief to the prior if the observation y at time t+1 does not make sense. Now, how do you do this? Well, you will use this base factor surprise that we have seen in the earlier video. You compare the probability of observing the new data point yt plus 1 under your current belief, that's this term here, and you compare this with the probability of observing this data point yt plus 1 under your prior belief. And then this is the base factor surprise, and the term gamma that modulates the learning rate is a monotonically increasing function of this base factor surprise. So this formula I show you here is exact Bayesian inference in a volatile environment. And so we see that exact Bayesian inference predict that we need to modulate with the update with the factor gamma, and this gamma depends on the base factor surprise. Now it turns out that this exact update rule is not implementable as such, but this base factor surprise plays a crucial role in approximate methods. I give you here 3: particle filters with n particles, message passing with n messages, other published approximations. They all use this base factor surprise, and this base factor surprise should modulate the learning rate. This modulation of the learning rate allows you to reset your belief if the observation y at time t plus 1 does not make sense.